Okay, so let me redo this question. I've done a version of this question before, but the version I did, the part was modified from the textbook, and when I read the textbook version of the question, I actually like the textbook version better. So the question you will see in your homework set is actually the original textbook version. So let me just redo this entire question so that I can replace that video with the one that actually matches the question you will see in your homework. So the question says, two boxes of mass M, A and B. Also, I think what it means is they both have mass of M each, I think, are at rest. Box A is on, let me just start doodling to make sure I get all the information. Box A is on level ground. I'm just going to label it as A. And box B rests on an inclined plane tilted at some angle, theta, with respect to horizontal. And this is box B. I hope there's a friction, otherwise B is gonna sliding down. Or I guess it doesn't actually matter if there's a friction or not. The kind of question they are asking us, it doesn't depend on whether they are accelerating along the surface or not. So let me, I'm gonna draw free body diagrams of them so that I can illustrate my understanding of the setup, and then I'll answer the questions. Because it's gonna be, reading ahead, I see it's gonna be asking me for the normal force. So, so the free body diagram of A is pretty simple. It's just the two forces, gravity pulling it down, mg, and normal force pushing it up, and let me call it sub A. And when you go through the analysis, it's not accelerating up or down. So really the only way it can work is if this normal force is equal to mg. And one caution I have for you is don't memorize this like a formula or something, because it depends on the situation. In fact, you will see for B that normal force there is not mg. But that's for A. A is a lot simpler. It's on a level ground, not accelerating, everything balancing out. Yeah. So for B, let me draw a free body diagram first. Now the number of forces, let me just make this easy for myself. I'll say the incline is frictionless. If it does have friction, it won't change any of the answers that I'm going to be writing down. It'll have gravity mg. And with the normal force, this is where I have to be careful. I have to remember the surface is not horizontal, it's at an angle. Normal force, the normal means perpendicular. So normal force always has to be perpendicular to the surface that's exerting the normal force, NB. So here, if there's no friction, then this is going to be accelerating down this way. That should be your intuition. Now, if you're somehow going to make it so that it doesn't accelerate, then you'd have to say, oh, there's a friction force that acts this way, something like that. Let me not have friction. And so it's accelerating. Now, so what I need to do is figure out what this NB is. And the one piece of information that you have. So I guess this week, am I doing full standard strategy? Let me do a quicker version. So the kind of questions they are asking me, I don't need a full standard strategy. So I'll just do abbreviated version of it, which is that here I'm going to make use of the fact that I do know this, if it moves at all, it's going to be accelerating along the surface. That's really the role of the normal force. It prevents the motion, into the surface. It prevents that. It doesn't prevent the things from leaving the surface, but that's another matter entirely. So using that, I can focus my analysis along this axis that's perpendicular to the surface, and choose to look at just that component of gravity. So I can break gravity into two components, component along the surface and component that's perpendicular to the surface. And I'm drawing this triangle because it'll help me figure out the expressions for these components. So this surface is at an angle theta, and I have to kind of think through the geometry here. This angle here is the 90 degree minus theta, so that's not theta itself, because I'm thinking of a right triangle that looks like this. Then that angle is 90 degrees minus theta. But having identified that angle, having identified this 90 degrees, this is the 90 degrees minus that angle, so this should be theta. I hope you are getting a lot of this geometry exercise, and at some point all of this will just come naturally to you. With this angle identified, now I can say I know my hypotenuse, that's mg. So this side, which I care about, that should be the adjacent side. So it's going to be associated with cosine from SOHCAHTOA. This should be mg cosine theta. So once I get this far, then I can say, oh, this must be equal to normal force, so that there's no acceleration perpendicular to the surface. So NB is mg cosine theta. So I think that's everything I need to answer the questions that they're asking us. They're asking for the expressions for the normal force acting on each block, okay? mg for NA, and mg cosine theta for MB. And my OpenMath understands implied multiplication. It does it by forcing question writers to define variables. So when it says mg, it knows it's m times g, not a new variable called mng. So compare the two forces, that is, find the ratio of NB to NA. I think I can do that in my head. mg's cancel out as long as their masses are the same. So this should just be cosine theta. And then if the angle of incline is 30 degrees, which force is greater and by what factor? The angle kind of doesn't matter for which is greater. The NA is always greater because cosine theta is less than 1 or equal to 1 at most. So NA will always be greater than or equal to NB. And for 30 degrees, oh, can I do this in my head? Cosine of 30 degrees. That's root 3 over 2. Root 3 is like 1.7 something. So this might be like a 0.85. Oh, wait, it's 1 over. So it's a 3 divided by, oh, that's harder. All right, let me just do it here. Force on A is greater by a factor of 1 over cosine of 30 degrees. Yeah, at some point I don't really want to do it in my head. I could have maybe guessed, I don't know, 1.155. So yeah, so that should be correct. Yeah. So this is the textbook version of the question, and I thought I liked it better than the other one with the modified part to see. So again, this is not a difficult question, but I hope this question teaches you not to automatically associate normal force as mg. If you've been somehow doing this, then please stop. You'll get confused by questions like this. And really, what I recommend is. So in the lectures, I have types of force lecture. In the lecture, I tell you the properties of each force. Normal force is the one of the two forces that's called constraint force. It enforces a constraint. Enforces a constraint that whatever object you are dealing with doesn't kind of dig into the surface. So using that constraint, your job is to figure out sometimes what the expression for normal force is. And the process for doing that is the standard strategy. Sometimes once you get used to it, you might be able to use an abbreviated version as I did here. But if you're looking for a formula for normal force, there isn't one. You have to do force analysis to figure out the correct expression for normal force in each scenario.